Als nächstes kommt Professor Henrik Svensmark vom Danish Space Research Institute. Henrik Svensmark ist bekannt geworden mit einer Arbeit von seinem, ja genau, mit seinem Doktorvater Egil Fries, ich kann seinen Namen nicht aussprechen, über die Wirkung von der Wolkenbildung, Cosmic Rays, was Svensmark-Shaviv gerade angezeigt hat, die Wolkenbildung als Folge von kosmischer Strahlung. An der Stelle möchte ich noch mal zwei Worte zum Thema Cancel Culture sagen. Die Forschung von Henrik Svensmark ist seit einigen Jahren von offizieller Seite so gut wie auf Eis gelegt worden, weil seine Forschung halt nicht das offizielle Narrativ unterstützt. Wir haben im Rahmen unserer Möglichkeiten, dank Spenden von Ihnen, versucht, hier einen Teil dieser Forschung weiter zu kofinanzieren, mit jetzt noch bescheidenem Einflussergebnis. Und also für den Fall, dass Sie wissen, wo noch die Forschungsanträge auszufüllen sind für weitere Forschung auf dem Gebiet Klima und nicht zwingend in Richtung Mainstream gehen soll, Anträge sind immer noch herzlich willkommen. Okay, Henrik, we're looking forward to your presentation about cosmic rays and cloud formation. The clicker is over there.
Okay, so all we need is the presentation. Thank you very much for inviting me again. I think I've been to almost all these conferences over the years, and we have been working on these ideas for many years, so it's really a big pleasure to show you some of these things again. It is a collaboration. I'm collaborating with one of my colleagues, which is Martin Enghoff. He's also at the DTU, the Technical University of Denmark. And then, of course, near Shaviv, we have been working together for, well, I mean, it's actually 20 years, more or less now. And then my son, Jakob Svensmark, and finally a postdoc, Irena, which works with NIR. So I'm going to talk about the connection between cosmic rays and clouds and why we think there is such a connection. And I'm going to give you the sort of the basic idea that we have been working on. And it of course involves what we call cosmic rays. So I will show you what cosmic rays are in this context. And then I will show you why they are important. And the whole idea, of course, has to do with that they affect Earth's cloudiness. And I will show you some results that actually indicate that this is the case. And then the final part is on these very long timescales that Nia also talked about. And that is over millions of years. And I will show you some influence on life. And these are some relatively new results I'm going to show you. So what are supernovas? Well, you see here that in the Milky Way we have stars, large stars that explode, and then they produce what we call a shock front. And the shock front accelerate particles to enormous energies, and these particles are then moving through the interstellar space, and some of them might actually go and get into our solar system. And as they go into our solar system, they meet what we call the heliosphere. And the heliosphere, it contains the sun's magnetic field, and this magnetic field it can actually screen against cosmic rays. That means that in periods where you have high solar activity, more of these cosmic ray particles are sort of scattered back into space, and you will have a change in cosmic rays. So what happens when the cosmic rays enters into the atmosphere. So you imagine we have the atmosphere here, and we have an incoming proton of maybe 100 giga electron volts, and you see you get this kind of shower structure. So one particle, instead of being just one particle because of the interaction with the atoms of the atmosphere, it can become to millions of particles that move down through the atmosphere. And this is something that is happening all the time. If you could see these secondary particles, you will see that we were sitting in a constant rain of particles which are entering into the atmosphere all the time. What is interesting is that these particles, they ionize the atmosphere, and these ions are extremely important when we are going to talk about the effect on clouds. And another thing is that they produce new isotopes. So the energy is so high, so we produce, for instance, carbon-14, which everybody has heard about. You use it for dating of archaeological artifacts of various kinds. And some of this slightly heavier carbon, it might go into trees and end up in tree rings. And then you can measure how much carbon-12 you have in a tree ring relative to carbon-14. And if you know that, you can say something about how active the sun was, how many cosmic rays entered into the Earth's atmosphere. So the interesting thing is that every time you have a change in cosmic rays, you apparently have a change in Earth's climate. Near showed you a number of correlations on longer time scales. Here is just one example. So this is the temperature over the last 1,000 years. And you can see here we have the medieval warm period, then we have the Little Ice Age, and then we have the modern warming. If you look down at the bottom figure, you can see how solar activity is changing, and you can see there is a nice correlation where you have, this is actually low solar activity during the Little Ice Age, and this corresponds to an increase in cosmic rays. So colder climate means more cosmic rays. Then this is what we see all the time. Okay. So the question is, what are cosmic rays doing to the atmosphere? And the idea that we worked on very, very early was the idea that if it's going to be an effective way of changing the Earth's climate or the energy budget of the Earth, it should be clouds. And you can see from this picture here, a beautiful animation, that you have clouds everywhere. And if you have a systematic change in these clouds, it will be a very effective way of changing the Earth's energy budget. You can see that the clouds, they cool the Earth with about 20 to 30 watts per square meter. So if you have a systematic change in the Earth's cloudiness, it will be important for climate. And clouds is really the dark horse in any climate assessment. This is the largest uncertainty in understanding climate change. Okay. So originally, we had this idea that it could be clouds, and this is the figure that also Near showed. So what you see here is a satellite data set from about 1983 until 2006. And the red curve here is the change in cosmic rays, and this is measured by neutron monitors. So these are instrumental measurements that we have here. And the blue curve is change in low clouds measured by this satellite data set, which is called ISKIP. And the reason the data only goes to 2006 is because it is extremely difficult to have a calibrated system because you have many satellites that has to be calibrated, and the changes that you're seeing are only on the order of 2%. So it's very difficult to have such a system calibrated. So after 2006, there are problems with the calibration of this data set. So what we saw is an apparent correlation between the two. It doesn't explain what the physical mechanism should be. So in order to understand how we sort of try to understand the connection between cosmic rays and clouds, we have to look at how clouds actually are formed. So in order to form a cloud droplet, you have to have a surface on which water vapor can condense. And this is given by what we call cloud condensation nuclei. They are on the order of 50 nanometers. That means that they are so small that you can't really see them. So if you have a nice clear day, you won't be able to, I mean, even though you can see very long, the air is actually filled with these particles. So they are always present in some number. So if you go over the oceans, then the question is, how are these particles actually formed? I mean, how do they get into the atmosphere? And it turns out that here they are produced by gases. So you have some gases with some molecules, and then the molecules stick together and produce what we call a cluster. This cluster might be on the order of 1 nanometer. And then over a week, this small cluster, it might grow almost 1 million in size or in the mass and become a cloud condensation nuclei. And the idea is that this ionization by cosmic rays, it helps the stabilization of these small clusters. So if you have more ions, meaning more cosmic rays, you're producing more of these small clusters, and if you have more of the small clusters, the idea was that then you get more cloud condensation nuclei. So that's the basic idea. And it's very easy to see that if you change the number of cloud condensation nuclei, you change the cloud properties. So if you look here, this is satellite pictures of regions of the oceans, and you can see it regions with low clouds, and then you see these stripes. And these stripes are where ships have been passing, and as the ship sails, it pumps out a lot of aerosols, and some of these aerosols can actually be used as cloud condensation nuclei because they are quite big. And you see that where you have more cloud condensation nuclei, the microphysical properties of the clouds are really changed quite a lot. You can see here they are much more white, so the reflection goes up. So if this can happen maybe in a smaller sense globally because of cosmic rays, it will be a very effective way. So if you change the cloud condensation nuclei, you are changing cloud properties. Okay? Right. So one of the things that we did was try to understand the microphysics. I mean, what is actually going on? And we developed things so much that we could test it experimentally. And we have been doing over the last 10 years, or even more than 10 years, we have been doing experiments. We have been doing experiments at the Technical University. We also started with the CERN experiment in Geneva, called the Cloud experiment. We also here in a period did experiments at an accelerator. So the accelerators are delivering these energetic particles that can ionize. And finally, we also had some period where we were down in a mine, 1.1 kilometer underground, and that was simply because we wanted to avoid cosmic rays. So you have to go almost 1 kilometer down in order to avoid the very energetic particle radiation. So all of these experiments, also the cloud experiment at CERN, they all get more or less the same result, which is as you increase the ionization, then then you produce more of these small aerosols, or the small molecular clusters. They are on the order of 3 nanometers here. And you see, as you increase the ionization in the chamber, you actually produce more of these cosmic rays. So one can say that there is certainly a mechanism that is producing these small aerosols. So as I just mentioned before, this very small aerosol, it has to grow to a cloud condensation nuclei. So when we made these experiments and we got these results, there were immediately groups that started to see if they could test these ideas in their global models, that is, in numerical models. And the thing is that if this little particle is somehow lost before it becomes a cloud condensation nuclei, then you can say there's no impact on clouds, and that would be the death of this theory. So what did these large models get? Well, these results is actually, I mean, these models have been producing results more or less from 2009 and until I think 1 or 2 years back. There were also some results, and they're all the same. And let me show you these results. So what you have here is the size of the small aerosol. So here it's 1 nanometer, and then it's 10 nanometer and 100 nanometer. When it's in this range here, it can function as a cloud condensation nuclei. So what they did in these experiments, numerical experiments, is to increase the number of small aerosols by maybe 5%, and then they look at the fate of these particles. So if it's going to affect clouds, you would expect that they grow up and end up, so you have as many particles here as you have here, then you will have a direct effect from the ionization. But all these models are actually getting the result as these particles grow, they disappear. So all of these particles, there are so few surviving to cloud condensation nuclei that they cannot affect clouds. And that has been seen as that was seen as sort of the end of the theory. So, and this is also what you read in the IPCC report today, that this theory is not really working. And you can see that it has been in the media, they have been very active to say that this idea has very little, I mean, it does not work. So you can see it here. So that looks pretty bad. But you have to remember, this is all in numerical models that you get these results. I will now show you what you get if you look at empirical results. So one of the things, this is the end of the theory that you had. So one of the things you can do is you can look at, if you look here, this is the sun in the middle, and this is the Earth that you have here. And what you see here is solar activity where some plasma from the sun is thrown out. And if this plasma hits the Earth here, you have one of the very, very strong events. If it hits the Earth, it will make the cosmic rays go down within hours, and it will stay down for a week or so. So this is how it looks. You can see here, then you have this explosion at the sun, you have this plasma hitting the Earth, and then you're measuring the cosmic rays, and it drops maybe by 30% within some hours, and then over a week, it sort of goes back to more or less the same level. So this is a natural experiment with the whole Earth. So we can then ask, is anything happening to the aerosols on Earth? Is anything happening to the clouds? And what you see here is different data sets. So Let me explain. Here you have day 0. This red curve is the minimum in the cosmic rays. So this is 15 days before the minimum, and this is 20 days after. And what you see here is actually aerosols, and you see you have a drop in the aerosols following this event. And then we have 3 different satellite data sets looking at clouds. And you can see in all of these that you have a drop, a quite significant drop. And there's a sort of a delay every time. And this delay is simply because the small aerosols have to grow to become cloud condensation nuclei. And that takes on the order of 5 to 7 days. So it all seems to be fitting very nicely. And the things that we have been doing is also to look at the energy budget of the Earth. So here you see the change in cosmic rays. So this is 15 days before. And then you have the drop in cosmic rays. So that gives you that this midline here is the minimum in cosmic rays. So what you have here is the latitude. So this is the equator. This is the South Pole, and this is the North Pole. And then you can see as the days goes on, then you have the minimum in the cosmic rays. And what you're looking at is data from what we call the Ceres satellite or Ceres instrument, and it's measuring the net change in energy that goes into the Earth system. So you see there is a large effect here on the order of 2 or 3 watts per square meter. And if you look down here, you can see that most of it comes from what we call the short wave. So it means that more sunshine is coming down to the Earth's surface simply because there are fewer clouds. Another thing you can see is that the effect is mostly on the southern part of the Earth, in the southern hemisphere. And here we see the zonal variations, but we can actually see it globally in the next picture. So what you see here is a map of the Earth. And what you have in this map is the change in shortwave average over a week before the minimum in the cosmic rays. And over here, it's the average in the week after the minimum. And you can see there's much more yellow in this map over here. So, and another thing you see, it's mainly over the oceans that this effect is strong. And finally, because you have much more ocean in the southern hemisphere, it's also mainly in the southern hemisphere. So it's an indication that you would like to have fairly clean conditions in order for this mechanism to work. So we spent actually 4 years trying to understand why these empirical results actually indicate that the mechanism is working and there's something wrong with these models. And the whole idea is that the cosmic rays are helping stabilizing these small aerosols, that's for sure. But they're doing another thing. They are actually accelerating the growth of these small particles so they grow faster. And the reason that they're doing that is because of these interactions that there are, what we can call them are enhanced interactions in the form of Coulomb forces and mirror forces. So the mass of these small ions, they are actually interacting all the time with these particles, and because of these increased or enhanced interactions, they can actually accelerate the growth of the particles on the order of 10%. And that's extremely important because that makes more of these particles surviving to become cloud condensation nuclei. Okay, so that was more or less the background and how we believe it works with respect to the microphysics. And what we have seen is that we have solar activity and it can modulate the cosmic rays on the order of 10%. And we have this cosmic ray cloud link, and it seems to be able to explain many of the changes that we have had over the last 10,000 years. And it will, of course, be important also in future climate, because we have to understand what the sun is doing in the future. And, of course, it will help understanding the historic climate. So the last part, I want to talk on completely different timescales now. Neil just talked about these on geological timescales, that is when our solar system is moving through our Milky Way, and we go in and out of regions where we have more or less star formation. And what I want to do is to show you that on these timescales, from millions of years to billions of years, there are huge changes in climate. And these changes are so big that they've had a large influence on life during this time. So, one of the things I'm going to, one of the ways that what I have to do is try to reconstruct how cosmic rays has changed back in time. And one of the things that, one of the ways that I've been doing that is by looking at what we call open stellar clusters. So what you have here is some gas, and the gas collapses, and that might produce a group of stars that are all bound by gravity, and they are all produced from the same cloud. So these are all sort of made at the same time. And this is the Seven Sisters or Pleiades. This is one of these group of stars. And if you look in a radius of 3,000 light years, you will have on the order of 1,000 of these open stellar clusters. And from that, I can actually reproduce the star formation. And when I have the star formation, I can say something about how much cosmic rays were produced as a function of time. And this is what you see here. So this is more or less the present time, and we go 500 million years back. And you can see you have this variation. The variation is now on the order of 300%, so it's quite a lot. So if we look now at the last 200 million years in this plot here, you can see the red curve is the change in cosmic rays, more or less. And then this blue curve and all the dots are reconstruction of temperatures. And you can see there is a very nice correlation. The important part is that the changes in temperature is maybe on the order of 10 degrees. So it's a change in climate on the order of 10 degrees, which is quite a lot. It's so much that it will be quite influential on the biology or life on Earth. So why is that? Well, one of the important things is for life, if you look at life in the ocean, is that you need nutrients of various kinds, phosphor, iron, and nitrogen. And that is actually delivered by river runoff, and then it gets into the oceans. And then if you have a large mixing in the oceans, that means that you get a lot of nutrients delivered to the biological system. So if you have a lot of nutrients, it means you can have a larger biosphere. And if you have a large biosphere, it means that you will also get more organic sediments. And then there's another thing which is important. That is that when you have a large biosphere, well, life would rather uptake carbon-12 than carbon-13. 1% of the carbon is in the form of carbon-13. So if you have a large biosphere, it means that you have that life has taken a lot of the carbon-12. That means that this ratio is changing. So by measuring this ratio in sediments, you can say something about how large the biosphere is and how much organic sediments were produced. So this work was published in Geophysical Research Letters, and much to my surprise, it even made the front page of the journal, as you can see here. So it looked as if it were new times for the things that we are doing, but I'm not so sure anyhow. But it was very nice that it made the front page at that time. So it's half a year ago. So the idea is that if you have sedimentary mountains, you can go here, this is Grand Canyon. You can see all these layers here, and you go in and you measure this carbon-13 to carbon-12. And that says something about the fraction of organic material that is buried as sediments. And what you see here is the change in cosmic rays from some different data sets. So this is the change that we have over the last 500 million years. This is all astrophysics, right? So what I'm showing you now is from these sediments, which is geology, and I will put it on top of this figure here. And you can see there is a remarkable correlation over this period, indicating that the supernovas and the cosmic rays have had an enormous influence on conditions here on Earth. So the thing is that when we have a large bioproductivity, we have a large fraction of organic material that is buried, and that corresponds to a high cosmic ray flux simply because you are delivering nutrients to the biosphere. Whereas if you have a low cosmic ray flux, you are not really delivering very much nutrients, and the biosphere necessarily is smaller, and you get less organic material buried in sediments. So this is the last 500 million years. It turns out that you can actually extend time back almost 3.5 billion years. So what you see here is the star formation in the Milky Way. This is 3.5 million years back. And you can see that there was sort of a peak here for about 2 billion years ago. Then there was a minimum for almost 1 billion years, and then you have things going up and down. We have just looked at this part here, where you see this is now, and then we had a minimum and a maximum, and then we go further back in time. So from sediments going that far back, you can also get the carbon-13 to carbon-12 and get the fraction of organic matter in sediments. And this is the curve that you get. And you see that you have this maximum here. You have this period where not so much is happening, and then you have this movement up and down. You see this beautiful correlation. You also see that glaciations are fitting fairly well when you have a high cosmic rays, yet when you have large ice ages during this time. So there is another thing about when you bury organic matter, and that has to do with the production of oxygen. So you have had photosynthesis for almost 3.5 billion years back, and usually, I mean, the way that works is that you have some CO2 that combines with water, and that gives you glucose, and then you have some free oxygen. But if you take this organic matter, you just leave it on the surface of the Earth, then the reaction will go back again. That means that the oxygen will disappear, and there will be no net production of oxygen. In order to produce oxygen, you have to take this carbon here and bury it as organic matter in sediments. Then you get oxygen to the atmosphere, or you get oxygen into the ocean. So this curve here with the fraction of organic matter is really also the production curve of oxygen over this period of time. So if this is true, that means that supernova has really helped the production of oxygen, and we all know that oxygen is needed for the evolution of complex life. So all of a sudden, the whole evolution seems to be connected to things which has to do with our Milky Way. So the question is, why do we have these large peaks here? Because these are not spiral arms changes, these are something else. And it turns out that that might actually be because of interactions of our Milky Way with what we call Dwarf Galaxy. There is one called Sagittarius Dwarf Galaxy. So if we are over here and we look towards the galactic center, so just below the galactic plane, you can see this Sagittarius Dwarf Galaxy. And if you calculate its orbit, you can see that it has interacted with our Milky Way. So if we look here, we can see between 6 and maybe 5 billion years ago, there was a very strong interaction, and you produced a lot of stars, and maybe our solar system was produced because of this interaction. But then if we go here, you can see there are some interactions, further interactions, and you see these starbursts here, and they fit very nicely with the two maximum I just showed you. So let me conclude. It seems as if variation in cosmic rays are associated with changes in the Earth's climate, and we have really strong empirical evidence on nearly all timescales. And the idea that we've been working on is that clouds are important. It's an important link between or two cosmic rays variations. And we sort of divided it into solar activity, which affect from days to 10,000 years, that is over the Holocene period. You see these beautiful correlations. And with the supernova activity, we see it over millions of years. And the last part was that when we put organic matter, this organic matter seems to follow variations in this supernova history. And it is the source of oxygen and therefore fundamental for the evolution of complex life. So if these things are correct, it seems as if this mechanism that we are talking about might be one of the most important mechanisms in the total history of the Earth. Thank you.
Oh, sorry. I think you don't need it. I would like to ask in English. First. Yes, I'm here. Thank you. I'm interested in your work, although I'm a lay person to that kind of research, and so I have a naive question. It concerns a small time scale, about 20, 30, 40 years. In the publications, in the time series of the German Weather Organization, you can look up the sunshine, the hours of sunshine, and this is almost steadily increasing has been increasing for the last 30, 40 years, and I don't see any 11-year cycle in it. And I think that applies also to Switzerland, Austria, maybe Denmark, Central Europe, and it's present in winter as well as in summer. Do you have any idea what may be the cause of this increase in sunshine hours?
Well, I mean, the solar cycle variations is something that Nir actually worked on, and he showed some figures where you saw that the energy that goes in and out of the oceans has this 11-year cycle, and it's almost a factor of 10 larger than what you would expect from solar irradiance. And I'm pretty sure you also see, I mean, you have done some work where you actually see solar cycle variations in the temperature data, right?
Well, you see the temperature data, but okay, so but over land, you don't expect to see a large effect of the sun because, as Henrik showed, most of the effect we see is over the oceans. So over the land, you have other effects which are dominant. You also see in the global temperature is the 11-year solar cycle, but again, as I mentioned, because of the large heat capacity of the oceans, it's relatively damp. So the temperature variations, the global variations in the temperature are of order 0.1 degree, which might not sound large, but it's huge actually.
Could you say something about chemtrails? Is there any effect of chemtrails in the clouds?
Of any effect of what?
Chemtrails.
Chemtrails? No, I haven't noticed any of that. Have you?
So geoengineering?
No, not at all.
I appreciate your work because I'm following this astronomical investigations since many years, but I have some concerns about your remarks about the glaciation of the Antarctica, because from the geological point of view, we know that the glaciation has taken place about 20 million years ago with the sinking of the land bridges and the thermic isolation of the Antarctica by ocean currents which are surrounding anti-clockwise this frozen continent. So I'm a little bit doubtful about your explanations, what you showed about in the Neogene in the Tertiary times. Maybe you can say something.
I can certainly say something. But I think the glaciation, according to a lot of these data, is around 34 million years ago. And there are various ideas of why it glaciated. What I've shown is, or what we have shown is that it coincides beautifully with the changes in cosmic rays over this period. And when you had the glaciations, you had first a glaciation, and then it started to melt. And then it reglaciated, and you actually see this in the reconstruction. You see this effect in the supernova reconstruction. It could be accidental, but at least it seems to be consistent. And I know that there are ideas about the straight opening, so you have these currents going around, and that's also part of the. That's one idea of explaining why Antarctica glaciated. So we will see.
If we fly in polar regions, we very often have aurora borealis. Is that a visual thing of this effect? Can you say something about it?
The aurora is not really directly related, because the aurora that we see is basically due to high energy particles coming from the sun, which are actually low energy compared to the cosmic rays. We are talking about particles which are at most a few hundred MeV coming from the sun, and because they are relatively low energy, they are funneled through Earth's magnetic field towards the poles, and then they are stopped at heights of typically 100, 150 kilometers. They ionize the nitrogen and oxygen, and when you get the recombination, you see the beautiful aurorae. The cosmic rays come at energies which are much larger. We're talking not about 100 MeV, but at 10 or 100 GeV, so it's 1,000 times more energetic, or 100 times, 1,000 times more energetic. And these higher energy particles affect the atmosphere at lower altitudes.
Also Sie können die Fragen auch gerne auf Deutsch sprechen, das wird ja alles gedolmetscht, also das muss nicht auf Englisch sein. Haben wir es geschafft? Okay, and then thanks a lot, Neil. Thanks, Henrik.